and welcome to Teaching Physical Sciences. Welcome, Bill.
How are you doing, Helen?
I'm okay. How are
It's
you?
just a fantastic start, Helen. Well done.
There we go.
We are really excited to have you here.
Thank you. Thank you. It's great to be back.
Yes, and welcome, Dylan. Thank you for pushing the buttons behind the scenes. Today we're talking about redox reactions.
We are talking about redox reactions.
I always want
11.
to call it redox, like the body soap.
Okay, hopefully there's no redox happening in that. But yeah, it does sound a lot like it.
Okay, but it is pronounced redox.
Well, I mean, it's a shortening of two words. So, reduction and oxidation. So where you put the emphasis, it's entirely up to you.
Well slipped in there. You see how I brought in that topic of conversation? The two words immediately coming into one.
Absolutely. Reduction and oxidation.
Yes.
There we have it.
Remember, you can talk to us using the hashtag MEScience. And that's, of course, if you're using Twitter. If you're not using Twitter and you're using Facebook, search for Digital Classroom South Africa and find the post, today's post. You'll see that it says types of reactions and 18th of September, 3 p.m. on it. Make a comment underneath that. Dylan will be watching both of those.
Like
now let's say you don't want to be on Twitter or on Facebook. There are some of us out there who value our privacy. And you just want to talk to us, you can do that by scrolling down on the screen that you're watching us on, and you'll see there's a chat box just
That's
below.
actually on the page?
Yes.
Ah, fantastic.
Very good. And you just type in a nickname.
Okay.
Any nickname, you press login, I think it is, and Dylan's watching that as well, so you're welcome to start a conversation with Dylan and throw us some questions.
Absolutely. We'd love to hear from you.
Yes, of course you can win if you do this. You can win 110 Rand Vodacom airtime.
Oh, nice.
Yes, and if the airtime doesn't inspire you to do anything, maybe a phone or a tablet will.
Oh, okay.
And the way you win those is by sending us an email at
fantastic.
competitions@digitalclassroom.co.za. You're very distracting with all of the
I'm sorry.
comments.
I just meant to stand aside.
Basically, we want to see a good teaching resource. So if you do something that's really, really exciting in this section and you want to tell us about us, tell us, because you could win a new phone or a new tablet. We're not giving away secondhand stuff here.
Oh, nice. Very nice.
Yes. The phone is a Sony Xperia L, and the tablet is a Galaxy Tablet 4.
Oh,
Galaxy
fantastic.
Tab 4, I think the official
fantastic.
name is. Yes. Well, there, I got through the bits and pieces, the introduction.
Fantastic.
And now you're welcome to interrupt as much as possible.
Okay. I particularly like this section. It's fraught with a lot of problems, though, so I'm glad we brought it up as a topic. It's not usual that it's usually addressed as a grade 12 problem because we only diagnose problems in the grade 12 year, and by then there's too many problems. So attacking it properly at grade 11 level is pretty important.
So CAPS has done something really good here by moving it down.
It has. There are a lot of sensible parts of the CAPS, especially in physical science. I think a lot of us are very resistant to changes to the syllabus. But
well, we're teachers. We don't like change.
Absolutely. But I think the shift from the revised NCS to the new CAPS document, especially for the FET phase, is a lot of it's actually really good sense. There's a lot of good science in there. And shifting redox, I've actually started getting a little bit of a head start and actually started feeding it into grade 10 level, especially with some of the terminology. So there's a couple of tips later on coming up about how to actually feed this into your grade 10 learners as well to plant the seed early.
Fantastic. Before we get too much into the nitty-gritty, I've been reading this book, Teach Like a Champion, the 49 Actionable Teaching Steps. We're on technique number 19 called at-bats. Now, if you're not American, it makes no sense to you. Or maybe there are people out there who play baseball who aren't American. So
Perhaps
if
cricket.
you don't play baseball, at-bats doesn't make sense. So I'm going to tell you baseball talk, and then you can tell me what it is in cricket talk. Because it sounds like you know cricket.
Yeah, absolutely.
Okay, in baseball talk, learn to hit by getting as many at-bats as you can. And they say at-bats is facing the ball with the bat.
Absolutely.
Yes, so cricketing terms?
Well, in cricket, I mean, you'll see a lot of the pro cricketers standing in the nets for hours and hours and hours, getting bowled the same balls again and again and again to try and work on a particular shot. They might do this for hours and hours and hours. Even pro golfers will stand in one spot and, even go after this again and again and again.
The same thing over and over
Absolutely.
and over.
The best of them do this. So,
And
I mean,
the thought behind it is?
well, a lot of science is habit. I know that science is a lot about understanding, but the part of writing good exams and the part of actually doing good science very often is getting into the best habits possible. Sometimes in sports, it's muscle memory. You don't even have to think about doing something, and you just react, and your body reacts accordingly. But a lot of people don't understand that the brain has got its own way of doing the same thing. You can exercise your brain the same way you can a muscle.
Okay.
So I think this is what they're after when they give this tip.
There's an educational theorist or something like that. She's got a fancy title called Melody de Jager. She's well worth reading. She's a South African, and she talks about forming the equivalent of muscle memory in your brain and doing something over and over again until it sticks. And what she says is the first time you do something, it's a little like bashing through a jungle.
Oh, yes.
You're going to put your feet down, but you won't leave a path necessarily. The second time, you'll remember the direction you must go in, but you won't see the path until you get to the destination. But as you do it more and more, your brain prioritizes that pathway and starts protecting it with a layer of good fatty stuff, not the bad fatty stuff.
Well, I believe it takes 21 days to start forming those pathways and cementing them.
Yes, and the more you do it, the more your brain prioritizes keeping that knowledge.
Well, absolutely. I had a long discussion with one of my students in class today. They weren't showing their working out while they were doing their practices, and they said, no, I'll do it in my exams. And I said, what you do in practice, you will do in exams. Getting into the habit now, especially with the repetition, it has got a value of its own, and especially with the section we're about to do today. Absolutely.
Yes.
As many different examples as you can, as many different angles, sort of reinforcing those pathways and those connections again.
Yes. Shall we take a look at your 3 pressure points?
Absolutely.
Okay, so the first one says students are sloppy and careless with charges. Okay, you could probably just stop with careless. Students are sloppy and careless.
Look, I mean, some of this they actually pick up from us as teachers as bad habits. I've had to correct myself in even the language that I use. I mean, for instance, the one that we're going to be using a little bit later on today, I mean, the way that you would say, take this symbol and talk about it.
So the symbol that's on the board.
Yeah, absolutely. And then the way that I would talk about this.
Can we have a shot of the board, please?
There we go.
Thank you.
So what I've got written here is a symbol for copper.
Yes.
And then copper again. But there's a mistake in my language. And the kids pick up on that, and they pick up those bad habits. The one on the right is not copper at all. It's a copper ion.
Okay.
And just emphasizing it, and they've picked this up from us. As teachers, very often you say, well, the copper turns into other copper. This is how the learners see it because it's Cu and it's Cu. And Cu is the symbol for copper. But one is an atom and one is an ion. And there's a very important distinction. And they say, well, what does it matter if there's a 2+? It's still copper.
Yes.
And it really isn't. It's a completely different substance. It behaves differently. And in this section especially, it's about the charge. I mean, redox is only about the charge. So if you're saying, what does it matter? Well, this entire section depends on that particular difference.
So it's really important that you're writing it down as a teacher and they're writing it down as well.
Well, not only doing that, when you're reading through the symbols to emphasize the differences, put emphasis on the fact that, I've got copper metal. So use the complete terms, copper metal, copper ions. What are they?
Okay.
Are they solids? Are they dissolved in the liquid? Try and contextualize it, because at the moment it's just writing on a board.
Yes.
And it's actually meaningless to most students. We can't expect them to go, well, it has to have meaning because it's in their test. That's a really bad reason to care about something.
Yes.
So I say, okay, well, I've got some copper metal here. Perhaps reach across and get some copper metal. I think I've got some over here. I've actually put it away, but we're going to bring it out a little bit.
Isn't that it?
Oh, there we go. I mean, here's the difference between, copper metal and copper ions. They are very, very different substances. One is a brownish metal. And Dylan was telling me, enough with the copper, but this is my favorite metal for doing demonstration stuff because it's got a really strong color. It has a macroscopic relationship with what's going on here. I've got some copper metal over here, and I've got a copper ion over here.
Yes.
I don't think anyone in their right mind is going to call these two things the same.
Yes.
So emphasizing it really sort of brings it home. And again, it's my favorite demonstration one. We're going to be using it twice a little bit later on today.
Fantastic. Your second point says students do not learn or understand valency and oxidation number rules.
Okay, well, that's part of my 5-point teaching strategy, is that very often we assume that they've retained everything from grade 10. And when I say retained, especially with something difficult like valency,
Yes.
I mean, it's not a layman's term. It's not used in the home. It's not something that sticks in the vocabulary.
Yeah.
So, I mean, if I was to say to someone, what is valency? Even after school, most people have forgotten it because it's out of practice. So they walk into a lesson on reduction and oxidation, and the teacher says, oh, okay, well, oxygen has a valency of -2 if it's an ion.
Yes.
And they kind of expect learners to go, oh, yeah, I know exactly what you're talking about. Let's carry on. And I think it's important to spend at least a lesson or two just revising the importance of charge. How do we get to a charge? How do we predict charge? Especially with ions.
Yes.
It's very, very important because it is all about the charge. It's all about moving electrons. And if students don't understand that difference, then you've lost them on step 1. And I'm pretty sure every teacher that's watching this has had that battle at the end of matric where they just say, what's your least favorite section of chemistry? Almost unanimously, redox.
Yes.
And this is probably the worst answered section in the matric finals when we mark. In fact, it is always reliably the worst. It's a real problem area. And for me, the root problem, again, is the grade 10 foundation in ions.
Yeah.
So, yeah, I mean, that's really it. Even in my grade 10 year, I've actually sacrificed from other sections that they traditionally pick up quite quickly. I've done nearly an entire term on aqueous chemistry and charges. So, I mean, that's huge emphasis, but it lays such good groundwork for later on.
Yeah. Your next point says teachers rely too much on methods rather than understanding.
I think that's a general thing, and redox really sort of distills it down to a point. I mean, I've got some mnemonics on the board here. I've got some shortcuts, and I've got some really nice ways of explaining things, but they tend to be crutches.
Yeah.
That's we say, well, here's the formula. Here's step 1. Here's step 2. And then learners go, okay, fantastic. I'm going to make up my own nursery rhyme that's going to tell me step 1, step 2, step 3, step 4.
Yes.
And they get into an exam, and the exam doesn't present it in the same way. They get thrown a curveball, to carry on the batting analogy. But they get introduced to the question in step 3. And they're saying, well, how do I get back from step 3 to step 1? And they know, well, it doesn't count in the same order as the method given to them by teachers.
Yes.
So this is really one of the nitty-gritty sections where they really have to get the concept before.
When would you introduce the tricks?
I would say later on. If you introduce the crutch, they never learn to walk early on. Right at the end, they say, well, isn't there an easier way of doing this? And they've gone through all the difficulty, and they've learned the hard methodology. Then I might say, okay, well, you might find this helpful.
They must hate you when you say...
Initially, yes. But I think they get used to it, though. They get used to the idea that you do the hard exercise first, and then eventually you get the easier shortcuts. And usually I just present it as a way of checking rather than the way to do things. In grade 12, they, of course, start working with the redox table, the standard table of reduction potentials. And that's actually a shortcut. I know a lot of teachers that say, no, well, they need to know it, and they get shown early on in grade 10. But then grade 10s very quickly start relying on that table.
Yes.
And again, that's just bad teaching habit from my point of view. Of course, I'm open to correction and learning. Others might say, no, well, they need to become familiar with it. But I think it's a form of exam coaching then rather than understanding.
Yeah. Okay, shall we go on to the 5-point teaching strategy?
Yeah, absolutely.
The first point says revise the grade 10 ions and ionization and valency of ions.
Okay, it's word salad at the moment, and it is to most grade 11s as well. If you ask
That's
them,
a nice term, word salad.
Yeah, absolutely. There's just every technical term thrown into there. And there are differences. It sounds like a lot of repetition in the same sentence.
Yes, it
does. So it's ions, ionization, valency of ions. And they all sound exactly the same, but there's important differences between them. So what are ions? How are they different to atoms? Ionization starts to deal with how do I make an ion?
Okay.
And then valency of ions is, well, how negative or positive do ions become? during that process.
So before you start with anything else, they need to all be on the same page with that terminology.
Absolutely. You'll find that learners have forgotten most of the stuff. They might pick it up as they go along, but I don't think you can rely on that. Of course, a lot of grade 10 learners move schools, and you get a lot of new learners, and you don't know what the previous teacher's done.
Yes.
Even when you receive a new group of students from, another teacher has taught them in grade 10, you don't know to what standard or in what methods or what tricks they've been taught up until that stage. So this sort of levels a playing field. And for this section, foundation needs to be rock solid first before you move on. I would say spend as many lessons as it takes.
Oh, really? That much is...
This really is the bedrock. There's nothing that you can do if they don't understand the section. It's starting with Shakespeare before they know the ABCs. Really learning to spell before you learn to read poetry.
Yes. Okay, the next point says introduce process of reduction and oxidation with iron and oxygen, in other words, rust.
Okay, well, absolutely. I really like this example, when something rusts, because it starts to, this is one of the hooks, making science relevant. You're saying, okay, well, you've all left something metal outside before when it's rained.
One of our very first webinars, John
Yes.
came in and spoke about physical and chemical change, and he spoke about rust.
Yeah.
And teaching it to grade 10. So if this is an example that you carry on coming back to,
Yeah.
it solidifies all of these processes, doesn't it?
Absolutely.
Or brings everything together.
Well, this particular example I really, really like because one of the processes we're going to be talking about is oxidation. And when they get taught that oxidation is loss of electrons, and they're like, well, why is it called oxidation in the first place?
Yes.
And this at least gives you a reason. You're saying, well, oxidation does happen when you put oxygen on things. And then you start to say, well, it doesn't always have to have oxygen, and you start to move away from oxygen being there. But discuss, why does the piece of metal change into something different? Why does it become brown or orange and flaky? Why is there a hole in this vehicle or this trailer or this drum outside?
Of course, if you're living down by the coast, it's a lot easier to see those kinds of things.
Well, absolutely. There's actually rust everywhere. In fact, I've got a crocodile clip here, which is rusted just by being in the lab. It's everywhere. The nice thing is everybody has seen some oxidized iron.
Yes.
And oxidized iron is, just rust. So when you introduce the idea that metal and oxygen can combine, what's actually going on in there? And that's a really nice starting point for this explanation. I would advise not writing down oil rig when they walk into class and just saying, this is what oxidation is. This is what reduction is. Once they've got that example inside their mind's eye, then you start to say, well, let's tell the individual story of what happened to the oxygen when it found the metal.
So you look at the macro first, to go back to Johnston's
Absolutely.
triangle. You talk about what it looks like, what it feels like, what it smells like, why do you
Absolutely.
think it happened. Then you move to the submacro or the micro.
Mm-hmm. Absolutely. And then you can start with the symbolic, the representation.
Okay.
Because when you start to tell it as a macroscopic story, it becomes a lot easier to grasp on a microscopic or a symbolic level. And I like to tell it that way and start off with that observation. Because very often the observation you're saying, okay, well, this is something relevant. This is something that I've seen. It conjures up memories, feelings. I left my bike outside. It's rusted. Or I put the wrong knives in the dishwasher. Now they're rusted.
Yes.
This actually conjures up real memories. And that's pretty important, especially for chemistry, because my biggest complaints, especially from learners that struggle with chemistry, is they say it's so abstract.
Yes.
It's so out of reach. Physics is so easy because I can pick up a ball and drop it. Chemistry needs to be contextualized in exactly the same way. And that's one of my big tips later on, especially for redox, because redox actually is probably one of the most common types of reactions. And even breathing and photosynthesis are completely dependent on redox. And when you start to sort of bring up more and more of those examples, it really becomes a lot more real for them.
Okay.
Especially your biology students, especially once they get to matric and they've learned oxidative phosphorylation, you start to relate it to other subjects.
Yes.
Your biology students really start to light up, which is really nice.
Fantastic. Now, how would you move from this to the next point?
Okay, well, this is where we start to play around with the experiments. Always my favorite thing is a hook, and to try and sort of captivate the information in a way that's visually stimulating. So, I mean, I've got a little bit of I know that Helen always moves back.
Yes.
So, I mean, I've just got a bit of a burner here because you can't actually light this fire using anything less than some sort of burner. So what I've got here is a little bit of magnesium, and this is sort of like sped up rusting. I particularly like this experiment because I get the chance to react a metal with oxygen in a very real and understandable way. So I've got my metal here, which is going to play the role of this. Well, at least the magnesium that's going to play the role of the metal, and obviously oxygen in the studio around us. And once they start reacting, the really nice thing about this is you can see that redox reactions very often give off quite a lot of energy. And this particular one, once I take it out of the flame, it just doesn't want to light, does it? Just to make our life difficult. There we go. Right, that really beautiful bright flame. There is quite a lot of ultraviolet light in it, so don't stare at it too long. Is a really nice tangible way of saying, okay, well, that redox reaction has happened here. Now the question is, what has actually happened? Well, this is where we start to use our words in our stories. So I've taken magnesium metal, which was a silver metal. I no longer have that silver metal. I've got this white substance. How did we get there? We reacted magnesium with oxygen.
Okay.
So you start to bait them into sort of making predictions, and you say, well, what would the substance be called? And I would suspect that, a lot of them might suggest magnesium oxide. They've heard these words before. They've practiced making these compounds in grade 10.
Yeah.
So we're saying, okay, it's magnesium oxide. Now you start to break it down and you say, well, how does it actually happen? How do we get from magnesium to magnesium oxide? What is the real difference here? And how can we relate this to previous knowledge in grade 10? And that's really where they start to go, well, how does it get to this where I've got this like crumbly white? And it's very, very different. I mean, this is very different
hot.
from a metal. It's cooled down quite a lot. Don't
Okay.
do that immediately. But you've now got this white substance, this white powder, and that's very different to the metal. And I like to show them this. I like them to, especially for the non-toxic chemicals, to actually touch them, feel them.
Yes.
Really sort of burns it in. And this particular one is very, very popular, especially now that they've all got cell phones. Get them to video it, which I particularly like, because they go home and they watch it again and again, and they want to show their parents and all their friends. They're like, look at what we did. And it sort of carries it home for them, which I particularly like.
Yes.
And that's something quite cool, because years from now, when they're sort of pulling through their videos, especially if they've got cell phones with them, use the technology that they got with them. It really sort of solidifies this. All of a sudden,
fantastic use of the phone, because you don't have to have a smartphone to do that. You can
Absolutely.
have a standard feature phone and you can record.
Yeah, absolutely. And now there's video available on all of them, and very, very cheaply so. So all of a sudden now you've got that repetition coming in.
Yes.
They'll watch the videos. It's multimedia. They'll talk to their friends about it. Their friend says, what were you doing? And they're asked to repeat the language, describe what was going on.
Yes.
And that for me is where the real science happens. Yeah, the details of filling out reactions is important, but it comes a little bit later.
Okay. So the next point says use ion electron method to make half reactions for making various salts, adding half reactions.
Okay, now this is directly out of the caps.
Okay.
Okay, now again, all with the technical language, with the jargon, which I don't particularly like.
Word salad.
It is word salad. Okay, a lot of science happens to be, I'm afraid. So now, how do we get to this oxidation is loss, reduction is gain thing? And this ties into the previous introduction of, we used some iron, we used some magnesium in that case. How do we actually get there? And using this ion electron method. Now, what I mean by using this ion electron method is you're telling a story. So what actually happened to the magnesium? And I'm going to make a little bit of space here, because we would have used oil rig for the previous one. And you would have introduced that's what was happening to oxidation. So oxidation is the loss of electrons.
Okay.
Okay, the question is, how can learners actually see this? And this is where we need to contextualize. So I'm going to rub this off for a moment. We're going to come back to oil rig in a moment.
Okay.
And we're going to make some space to make some stories about magnesium and oxygen. Okay, so a lot of learners are saying, well, what happened to magnesium as it went from being a metal to being a compound? And this is where most of them will be able to at least give you, well, the symbol for magnesium, at least, is Mg. I've got some oxygen as well. And this is where you start to bring in the valency from grade 10. It's absolutely important that they can say that, well, magnesium oxide has got a formula of MgO. Now, there's a huge amount of skill in being able to say that that is magnesium oxide and being able to get the right formula. Because magnesium has a valency of +2. What does that actually mean?
Okay.
And oxygen is -2, so there's one of each.
Yes.
Now, there's layers of difficulty in that. Teachers don't realize how difficult it is to write a formula like this. It assumes so many things. So when I've got this, and once I've balanced this out, a lot of kids will be really sharp and say that this is not a balanced reaction. Let's tell the individual story of the magnesium and then the oxygen, which I particularly like, because this introduces the idea of the half reactions. So half of the story belongs to magnesium, half of the story belongs to oxygen.
Oh.
So let's tell the story of the magnesium. So
Okay.
when the magnesium goes from there to being inside the compound,
Is the word story used often with teaching it?
Not
Half
at all.
of the story. Because it adds a friendly element that makes it feel
that's the
attainable.
Friendly.
Yeah,
Yes.
well, absolutely. Redox is not spoken of in kind language.
No.
Learners are usually swearing about it or complaining about it, and when you're starting to disarm them and you're saying, "Well, what happened to the magnesium?" That's an invitation to tell a story. So that's why I like to use the word story. I don't know that it's that common or technically correct, but 90% of your learners are not going to become scientists, and the
Yes.
ones that are will latch onto it and understand the meaning behind
Yes.
it. So start to investigate, start to revise the grade 10 knowledge that says, okay, well, magnesium at the moment, if it's a metal on its own, if it's an element, it's neutral, and it has a charge of 0. The number of protons and electrons are equal to each other. Once it's inside a compound, something has happened to it. It's become an ion with a +2 charge. Now, the only way that you can get to there is by the assumption of knowing that magnesium, that's what metals do when they make compounds. Metals like to become positive ions, and because magnesium's in group 2, again, there's layers and layers and layers of knowledge that you're
Yes.
assuming to be correct. There's so many details, and just knowing that it goes from 0 to +2 is the starting point. Okay, so if I start my separate story here for magnesium, and I'll make one for oxygen. I'm just trying to get around the mic here. So I've got magnesium, which is turning into now a magnesium ion. Now, this is what's happened to magnesium. The question is, how did we get there? Before we get to the how, I want to tell the other half of the story, and then they interact with each other. So on the other side of the story, we've got a story of oxygen. And I like to change colors because they're two separate
I'll leave
stories.
this off for you.
Yeah, absolutely. We're going to get there in a moment. Okay, so we've got oxygen again, which is an element, and it starts out with 0, and it changes into a -2 in terms of valency.
Okay.
Again, with the grade 10 knowledge. So let's have these two stories side by side with each other. So I've got oxygen, which now changes into an ion, which is O2-. So we've got these two half stories or half reactions, and that sort of disarms the fear that they see when you've split up a reaction into two. I particularly like this because it's going to show us the way of writing the ion-electron method.
Okay.
Now, and you'll notice a couple of things that are wrong with the way that we've written this.
Yeah.
Written. Okay, with the magnesium, first of all, a lot of kids will say, okay, well, the magnesium is balanced. But the other thing that they're not aware of is that chemical reactions need to be balanced in terms of charge as well.
Yeah.
Now, here's the number one rule that I like to give learners, is that to balance charge, you can only add electrons to the one side or the other side. That's the only thing you can do.
Okay.
So if you add everything up on the left, on the magnesium, it's 0. But on the right, it's 2 positive. And the only way to get rid of the 2 positive is to give it 2 electrons to balance it all out.
Okay.
So I've got 2 negatives, 2 positives, and that all adds up to 0
Yes.
on the left and on the right. Now, the oxygen reaction has got a number of problems with it. The first one being that the atoms are not balanced themselves. I've got to have 2 oxide ions to balance out the atoms first.
Okay.
Now, this one's a particular challenge. How would you balance this out? By adding electrons. We can't add them to the same side with the negative, because obviously that would be making the problem worse.
Yes.
So now adding them to the other side gives us balance. There are 2 negatives on the left and 2 on the right.
Okay.
So this is the ion-electron method.
Yeah.
Now, this is very symbolic and very abstract, so we need to tie it back to a story. What was the role of the oxygen? What did the oxygen do? And you personify it. What did the oxygen do to the magnesium? Oh, it caused the magnesium to undergo the loss of 2 electrons.
Oh, yes. Okay.
So does that make sense?
Yes.
Now there's interplay. So what did the magnesium do to the oxygen? Well, the magnesium gave the oxygen its 2 electrons.
I can see, though, why it would be so confusing.
Absolutely.
Because it's added there, but still it's giving...
That's the other problem. How is magnesium losing electrons if it says plus?
Yes.
That is another one of the sticking points. So it comes down to how you're reading chemical reactions. Now, in the beginning, I think we've still got a little bit of gas.
Yes.
Okay. Right. In the beginning, I've got magnesium, which is neutral. And there, on the other side of the reaction, what comes out of the reaction are 2 extra electrons. They must have come from somewhere. Something lost them along the way. Now, this is one of the other teaching tips that I like to give is, even if you're not asked for them, and this is down to the repetition, always label your reactions.
Okay.
So if I don't identify that magnesium has undergone a loss of electrons, remember with oil rig, that oxidation is loss, and color-coded with our reactions, reduction is gain of electrons. Okay, so magnesium has lost these electrons, so I like to label that with an oxidation half. Just for my own revision's sake, and for theirs as well.
Okay.
Because they need to get into this. Then with the oxygen, has the oxygen gained it? It's far easier to see that oxygen has gained because I put 2 electrons in.
Yes.
They didn't come out. So something must have gained them.
That's a really nice way to phrase it. I put 2 in, they didn't come out.
So yes, they've gone into the pot and they're gone by the end of this experiment. They must have stuck to something.
Yes.
And that would be our reduction half. Now, no matter which example, and we're going to do a couple of experiments later on, no matter which example, I always try to split it up to the 2 different stories.
Okay.
It gets rid of a lot of the fear that they have for splitting up. I mean, these half reactions are very weird because it doesn't look like anything understandable is actually happening.
Yes.
But, yeah, well, look at all the symbolism over here. There's so much going on, but unless it's done in steps, try and color-code it if you can to try and separate out the stories. So we've got reduction in blue, the story of the oxygen, oxidation in red, the story of the magnesium.
It makes a lot of sense, the way you've explained it and the way, because it is potentially very confusing.
Well, absolutely. And also this is another thing that starts to happen. This first lesson takes about 1 lesson. And if you have 1 child daydreaming in this 1 lesson, it's going to cause you 6 weeks of catch-up.
Oh, my word.
It's such an easy concept to miss, and that's why you've got to repeat this and revise your skill set here.
Yes.
You can't only explain this once, because out of 30 kids, you're going to have 5 or 6 that are not hugely interested at the time, no matter how many tricks or experiments you do. They're not going to listen to you.
Yes.
For some or other reason. You have to re-explain this many times.
So every time you do any kind of redox reaction, you do the half stories.
Absolutely. Explain as if they've never heard it before.
Yes.
And with a preface to the kids that have really got it, I often tell them to try and engage them a little bit, adopt some people around you that don't understand. And then sometimes, very often for a section like this, they can code switch a lot better than you can because these are their peers. They use the same language. And very often they'll explain it in a non-threatening way.
Yeah.
And it's very encouraging to see that, your peers got it. Sometimes it's threatening. You're saying, well, they got it before I did. And if they become your mentor, your teacher, it reinforces both. It makes your job a lot easier. And not all the learners are that happy to approach you with this problem. Because they're saying, well, some people got it.
Yes, and so I must be stupid because I haven't got it yet.
Absolutely.
Yeah. And then you've got those who lie because they don't want to appear stupid and meanwhile.
Sure, they want to keep you happy. And that's a major problem, especially with this section, because you won't diagnose this until matric again. And it's such a tiny section in grade 11, it's foundation stuff.
Yeah. Okay, the fourth point, introduce rules for assigning oxidation numbers.
Okay, now this is where the rote learning and the repetition does work its way into redox.
So this is the at-bat section.
Absolutely. Those rules are absolutely vital. I know a number of grade 12s that once they've started learning the shortcuts that we teach them in grade 12, they learn not to assign oxidation numbers. Now, there are a couple of tips and tricks I'd just like to share to try and disarm some of the misunderstanding when you are assigning oxidation numbers. I'm not sure how we're doing on time. Do you know?
We've got 25 minutes left.
Oh, fantastic.
Yeah.
Time for some more experiments a little bit later.
We're doing great.
Okay. Now, some of the rules for assigning oxidation numbers, especially when you're about to get kids to do something which can be seen as boring or difficult or that requires a non-intersect section, you have to give them a really good reason to be able to do this. And when you say that this is a really important tool to figure out when redox has happened, how do I start to investigate what happened to each individual atom? Now, for instance, one of the reactions that I like to show them is that some elements don't behave. They don't behave in the way that they should. They don't correspond to any of the rules that I've learned before. I'm just going to write in blue because I think it stands out a bit more. So, for instance, one of those elements that doesn't behave is that sulfur. Especially when you take sulfur and it's sulfur dioxide. Now, sulfur can link to a number of different oxygens, and we can keep on adding oxygen to it. And here's another chemical reaction. This one becomes really important in grade 12. Let's actually get rid of the reversible bit. Let's keep it simple for the moment. So sulfur's not behaved. It's got two distinct personalities. Sometimes it joins to 2 oxygens, sometimes to 3 oxygens.
Yes.
Okay, of course it's not balanced at the moment. Some of your kids will be quite quick to point that out. And you start to say, well, what actually happened to oxygen? If you were to tell the story of oxygen, how would you know? Sulfur's already oxidized here, and it's oxidized over there. So how do I tell what's actually gone on? What is the story of sulfur? So just a couple of really important points. When you're trying to figure out the oxidation number of sulfur, there is a simple algebraic trick, and this is a really important one. This one actually teaches them to sort of dissect what's going on. What is inside SO2?
Okay.
The problem with elements which don't behave themselves, which don't fit into the valency boxes, sulfur is in group 16, so therefore it must be, is to teach them, well, sometimes you do know other things. There are reliable elements. Oxygen is fairly reliable. I know that oxygen usually makes a -2 when it's inside a compound. So we use what we do know to find out what we don't.
Okay.
So we make a simple sum, and the sum looks like this. Sulfur is the unknown, so I'm going to just use it as a variable, as we would in algebra. Plus 2 oxygens, and we know that oxygen, and this is one of the rules that they need to know,
is
that oxygen is -2.
Yes.
Now those two added up, especially if this is a neutral compound, should add up to a neutral charge of 0. All of a sudden it becomes very simple algebra.
Yes.
And then if we solve for sulfur, sulfur becomes +4. And that's the oxidation state of sulfur. It's really not a complex one. Now if we do the same thing for SO3, you'll find that sulfur has changed into +6. So it's a really simple diagnostic. I'm just going to do this again for any teachers that don't know this method. So just sulfur plus 3 -2 charges equals 0. I'm hoping you can see this all.
Yeah.
Yes.
Okay. If we solve for that, we take the -6 across. Sulfur becomes +6. So sulfur has gone from being +4 to +6.
It's a really good technique to have it underneath each particular section.
Absolutely. I like to sort of line it up with these. And this is what you should be doing on a board as well.
Yes.
Especially for their notes if they are taking them.
Yes.
Now, this does bring back into... Now, this I particularly like because it allows us to explain why there is a word called reduction. When we are adding electrons and we are reducing something, that doesn't seem to make a lot of sense to a lot of learners. That's understandable because the word reduction means making smaller. And what I'm going to do is I'm going to tell another story.
Okay.
And this story involves chlorine and sodium. This is probably the first ionic salt that learners talk about. So if I take some sodium and I add it to chlorine, for instance, and it becomes table salt, NaCl. Almost everyone knows this one. It's a nice, safe one to start with because they're so familiar with it. Now, what actually happens to chlorine? Well, initially, chlorine, because it's an element, has an oxidation number of 0. And that's one of the rules that we need to know. But once it's gone into a compound, we know that chlorine, because it's in group 17, or it's part of the halogens, it becomes -1.
Yes.
Now, you bait them into the answer. What has happened to the number? Has it increased or has it reduced? And this is where the number reduction actually comes from. If the oxidation number has decreased, it has reduced, and this is reduction taking place.
That's a really good way to...
Well, to be honest, I actually only figured this out after 6 years of chemistry. I never actually knew the answer to this. It's only when I started teaching, that I actually learned that reduction is to do with the making smaller of the oxidation number. And allows us to tie back, why are we learning this word reduction? Reduction is gain. That's what Rigg says, but that doesn't actually tell me why I'm using the word reduction.
Yes.
So this is one of the things to bring oxidation numbers to life. So you're saying, well, this explains something.
That's fantastic. Are we ready to move on to the next point?
Absolutely.
Okay, point number 5. Break net reactions into half reactions.
Well, in a way, we've already started it by the stories. So something really good to do is to give the learners a really, really simple demonstration, then ask them to tie it together themselves. So what I've got over here is, I've got a test tube rack here.
Give me.
Thank you very much. Okay, so I've got a test tube rack over here, and inside these solutions, I've got copper chloride, and that's a really nice blue color. The reason I like copper is because you can see when there are copper ions in solution. To my knowledge, there's no other ions with this particular distinct color.
Okay.
Cobalt comes close, it's really deep blue. But I like to have macroscopic observation. Most of the other metals make colorless ions, and that's boring. But we can take advantage of that, because if I do make other ions, they don't interfere with the observation. So the example that I usually give them, and this is a particularly nice one, I've got some magnesium powder inside here. So we're going to take some magnesium powder, and I'm going to add the contents of these two together. Now, this one's quite a quick reaction once you get it going. Magnesium powder reacts quite quickly, and you can see it's bubbling really, really nicely. Okay, now be careful about magnesium powder. It can make hydrogen gas and explode. I can see Helen stepping back there. Okay, now as this reacts, magnesium powder has got this beautiful ability to reduce things. Okay, it's a reducing agent.
Okay.
Now, what it does is it causes reduction, and we'll see that this reaction is starting to lose its color.
Yes.
The blue ions are starting to vanish, and it's really, really nice to demonstrate to them that the copper ions are actually vanishing. You are starting to lose copper 2+, and we're going to let this calm down for a little while, and you don't have to worry about me blowing up the studio.
And when you're saying these kinds of things, you go back to the thought that reduction is a loss in value in terms of the oxidation number.
Correct. So copper had a positive value of 2. Now it has a value of 0, and I can start to see the copper metal actually forming there. And the way I recognize that...
So the copper ions had a...
Correct. Okay, so the copper ions, which have a positive 2 charge, have now become copper metal. And the reason I can see that there's actually copper metal is there's actually brown powder starting to form at the bottom of here. Now, this demonstration I don't like to give to the learners because magnesium reacts quite vigorously. Okay. And this one can obviously bubble over. There's nothing toxic in it, but magnesium powder and water sometimes can be very, very vigorous. But as you can see, the copper ions are starting to disappear in solution. Now, here's a slightly simpler and safer option. Now, instead of using magnesium, I've got zinc granules.
Okay.
I particularly like these zinc granules because they're quite fun to actually see the consistency of the metal, and they're really nice and shiny. So I like shiny things.
Yes.
Okay, now I really like this one because this one's nice and slow, and you can actually start to see what happens. Now, I'm not sure what you can see on the camera there, but I've got these really shiny zinc pellets. And as I drop them in, almost immediately, it changes black and it gets coated in another metal. I'm going to do another one just to sort of emphasize what's going on here. So I've got this really darkly colored metal forming on the surface of the zinc.
So it's not the effect of the color of the solution.
Well, if we leave this long enough, and we're going to, we'll actually start to see that the blue color disappears.
Yes.
And these pellets get smaller. These pellets actually vanish. And that really sort of intrigues kids who's saying, well, nothing seems to be happening except there's something really odd. They're starting to get a bit fuzzy on the surface. Something really strange has happened. So I'm going to do it again, and you can actually start to see the observation. And you can see that as it slides in, almost immediately.
Yeah. Now that I know what I'm looking for, I can see that it changes.
So as you slide these in, they start out nice and shiny.
Yes.
Can you
And
put half in with the tweezers and then just pull it out again?
I probably actually could. Let me get a nice long one for you. And that's a particularly nice one. And let's see if we can get it right down into... There we go.
We're on this camera over here.
There we go.
Yeah.
Right, so let's not tilt that.
Okay.
Let's get a proper coating. And you can actually start to see that I've got this half-coated zinc pellet.
Yeah.
It looks
Now
like it's been dipped in paint.
Yes.
Absolutely.
Dipped in paint.
Okay, now if you actually rub off that, and it's non-toxic, you can actually start to recognize the brownish color of copper. And we can dip that in fully and let that react for a little while. Now, since this is non-toxic, I'm going to jam it up with my finger. And if we shake it up a bit, something really cool's happening. You can start to see that there is absolutely no blue color anymore.
Yes.
And if we let it settle out, you can start to see the brownish color of copper metal being formed at the bottom there. And these pellets start to disintegrate. And this one's really, really nice because you can start to see, well, something has definitely happened to the copper. I don't have blue ions anymore,
Yes.
but I do have copper metal. So the copper has changed from positive to 0. It has been reduced.
Yes.
But then...
It'll make sense now. Amazing.
Yes.
And then, you start to say, well, how? How do you just reduce? How do you just, you don't go down to a microscopic level and tell copper, you reduce your number.
Yes.
Something else must be doing the reducing. So we call that the reducing agent.
Okay.
And in this case, we've used zinc to do the reducing. Zinc has told the copper to reduce.
So you talk about things being reduced before you start talking about reducing agents.
Now, the problem is that reducing agents get confused with reduction reactions. They are linked. But there's a really nice analogy that I like to use. And now that this is settling, you can actually start to see that the blue color has vanished. And we've got that beautiful copper settling down at the bottom there.
Yeah.
And I like to explain it this way, is that an agent is not something that actually wants to participate itself. Like a sales agent is not particularly interested in buying products.
Yes.
They are there to cause a sale to happen. So a reducing agent is there to cause reduction to happen. It doesn't undergo reduction itself.
Okay.
So to tie back into this analogy, so chlorine, what is it? What is happening to it? The number is being reduced. What is causing that reduction in number? The sodium. So the sodium is the reducing agent. It is
Okay.
causing chlorine to undergo reduction. Now, how does it do it? Well, oxidation has to happen for that to happen. Now, this
Okay.
is the confusing part.
Oh,
So-
now we get to the confusing part.
Well, here's the quandary. Here's the problem. Let me actually use a different color to stop some confusion. Sodium, because it's an element, has got a 0 oxidation number. There we go.
Yes.
Once it's inside a compound, my rules tell me that group 1 elements have got a positive 1.
Yes.
So sodium has undergone oxidation because its oxidation number is increasing. But it's a reducing agent.
Yes.
So reducing agents undergo oxidation to do their job.
Okay.
So that's where the switch comes. A reducing agent will always undergo oxidation and vice versa. An oxidizing agent will always undergo reduction.
I don't think that's that confusing once you've explained that the reduction is not a reduction in volume.
Yeah.
Because that's what I always thought it was. It's
Well, in cooking terms, a reduction
Yes.
means that you boil off the water. So you're saying, well, do I boil off the copper? Definitely not. The copper's just changed into a different form. So I've changed from copper ions, which were blue, into a copper metal, which is down at the bottom.
It's pretty amazing.
This is my old favorite as well, the electrolysis of copper chloride.
Yes.
This one I particularly like because this actually changes back from elements back into ions. So over here, I'm not sure if you can see this. Let me actually move this a little bit closer. Let's try not to burn things down or
Please not.
leak any chemicals anywhere. But the electrolysis of copper chloride is a really beautiful one for teaching basic redox chemistry. And I'm not sure what you can see from there. So I'm going to switch on some current over here, and we're going to start to see some things happening fairly shortly. Right, now the reason I particularly like this one, and you can leave this one going for quite a long time.
So just to talk people through, you've got sticky tape on the sides to hold the electrodes in place.
Yeah, absolutely. The reason I like that is because then you can see the entire electrode and it gets out of the way. You can use press stick. The problem is as soon as press stick gets wet, it doesn't stick to things anymore.
Ugly. Yes. Carry on. Thank you.
Now, this particular one, if you are going to leave this for a really long time, please do it in a fume cupboard because you are going to be making copper metal from copper ions, and you're going to be taking chloride ions and making them into chlorine gas.
Yes.
And that's never a good thing to have a large amount inside your classroom. We're inside a sealed studio here, so I'm not going to be leaving this experiment going very long.
What qualifies as very long?
We're going to do it for a little while because I'd like you to be able to see that there is a change going on.
Okay.
Again, the reason that I like to use blue ions is because the blue will eventually vanish. If I'm changing blue ions into brown metal, we can see that.
Okay. But
now,
if I'm a teacher in a class, how long should I leave this running before I say, okay, let's call it?
Look, I mean, if you can run this inside a fume cupboard or at least next to a couple of open windows, you should be absolutely fine.
Okay.
If it starts to smell like really strong bleach in your classroom, it's a safety risk.
Okay.
Even now, I can start to get a faint whiff of chlorine sort of washing over. It smells like a swimming pool at the moment.
Okay.
And if you get really close to this and you smell too much chlorine, eventually you start getting a headache, which is not great.
No. Carry on. Thank you.
I mean, this again is a very macroscopic way of saying here is a chemical change taking place. I have changed blue ions into a brown copper metal.
Yes.
So I've actually undergone a chemical change there. And the same with chloride ions. Chloride ions, you can't see them, but somehow magically I've got a gas appearing over here which smells like bleach.
Yes.
And again, that's something that they've smelt before. They've smelt pool chlorine before. They've smelt bleach before. So we start to tell a story. Then you start to break things up again. So this ties in with our last point. So what I'm going to do is I'm just going to push that back for a moment while it busy electrolyzes and make sure that our entire studio is filled up with chlorine.
Yes.
Well, we'll be very
Sick day tomorrow.
Well, we'll be very germ-free.
Yes.
Chlorine's very good because it kills germs, but it's also good at killing people. So don't leave this running too long, please. I can see everyone's starting to get nervous again.
Yes.
Okay. The really nice thing about this is you can start off by revising that in solution I've got copper 2 plus ions, which are aqueous, and that's that beautiful blue color. Good time to revise phase symbols as well.
Yes.
And inside copper chloride, I've got 2 chloride ions. So this is what we start off with. And after the reaction, I've actually got copper metal, which is a solid, plus, and let's just make some more space over there. Look at big fat writing. And I've made chlorine gas. So that's really nice. You can actually revise the phase symbols with them. Aqueous just meaning that we've got this dissolved, and obviously solid and gas are fairly self-explanatory. But the question is, what actually happened? What are the stories that took place here? I took copper, which because of its charge, over here its oxidation number was positive 2, and I changed it into an element of 0. So the number has reduced.
Yes.
If you tell this as a separate story, it becomes even more obvious. So 2 plus ions change into copper metal. Now this is the ion electron method that we're going to do here. So now I've got my story. What happened to the copper? Now check, are the atoms balanced? Yes, they are. Now add electrons to make sure that the charges are balanced. Okay, so how do I balance this? Well, if I add electrons, the only place I can add them is onto this side where there's positive ions. Just do a final check. It adds up to 0. It adds up to 0.
Okay.
And then we start to tell the story of the chlorine. So chlorine, what color should we make chlorine? Let's make it green.
Yay. That makes sense.
There we go. All right, it is actually a green gas. I didn't even think about that. So I've changed from -1 because that's its formal charge in the ion. It's changed into an element of 0. So I can definitely see that this number has increased.
Yes.
So chlorine was oxidized by what I did here. So let's write out our ion. There we go. So chlorine ions. Let's keep the atoms balanced because they were already.
Yes.
So the atoms are balanced, and that's always something that you should check. Next thing to balance is the charges, and I see that the charges are unbalanced. Where should I add electrons? There we go. You've already cottoned onto this.
Yes.
So there we go. We've got 2 electrons over there. Now, a lot of them might not say, well, I'm only changing from -1 to 0. Why 2 electrons?
Because they're 2.
Because there's 2. Okay, so I actually sometimes have to draw the little bubble diagrams to actually show them, okay, well, there's 1 chlorine with an extra electron. There's another one with an extra electron. If I take the electron off each one, there's 2 electrons. And this is telling the 2 separate stories. Identifying as oxidation reduction becomes eventually habit. Now, this is one of the shortcuts that they quite quickly figure out, and I try and discourage. They quickly figure out that if I write electrons on the left-hand side, it's reduction.
Yes.
If I write it on the right-hand side, it must be oxidation. And I really don't like that because that encourages them not to understand and not to revise.
Okay.
So I actually say, well, that might be a good check, but why? Always challenge them, sort of back them down to say, okay, that's fine. If you want to use that as a check, our electrons are on the right-hand side. That and ask them to explain, because a lot more of the CAP-style questions are explain, justify, not just what is.
Yes.
And do this with as many examples as possible. Other challenging ones are, okay, well, we started with rust, let's end with rust. So describe to me, what is the story? How do I make rust at home? What is the process? And then this starts to churn their brains. They start to saying, well, what do I need to make rust?
Okay.
Well, I need iron in the first place, or something steel, and then oxygen. And what is the product? Well, it's Fe2O3. You can sort of cue them, and you say, well, what happens to the iron? Is it oxidized or is it reduced? And they can start to break it down for themselves.
Okay.
So, yeah.
We have 2 minutes left.
Okay, well...
So do you want to talk through what's happened over there? Or?
Okay, well, what's actually happened over here, and this is particularly nice. I'm sure that you can start to see that there's actually a really nice big brown deposit happening over here.
Yes.
Okay, and...
Bring it closer if you can.
Yeah, absolutely. Let me actually unplug this. Okay. No, we're not going to be able to unplug that at the moment. It's not letting go.
And
there we
hooking the crocodile clips?
We can do that, actually. That's a smart idea.
She's a thinker.
Absolutely. Problem solver. So there we go. We can start to see that there's a solid forming at this side. And I don't know if you actually noticed, the solution while we've been talking has actually become a lighter shade of blue. So what has actually happened over here is we started losing copper ions.
Oh, yes, you can see.
And they started changing into metal. And if you leave this long enough, at a nice low voltage, leave it at about 2-3 volts overnight, you'll actually find that the next morning you'll just have this brown solid, and the solution will be completely clear. All of the copper's been removed.
Yes.
And they say, okay, well, what difference does this make to me? And this is actually the method that all copper is refined. All the copper that is mined and refined is refined in exactly this way. They don't use the chloride ion, but they use sulfate, copper sulfate.
Okay.
Oh. And copper money, copper wires, all of that copper is produced.
There's lots of money in copper.
Absolutely.
Yeah.
I mean, people steal it for a reason. It's expensive stuff. And, this is the method that they use to refine and purify it.
It's good to know. Any parting comments?
Any parting comments? Please don't start with the redox table. That's one of the problems is I said that teachers like to get stuck in shortcuts, and that's one of them. Start out with this big complicated table, teach them shortcuts and hacks for how to use it, and they will sometimes get things right with it, and that encourages bad habits. So, teach them the methodology, tell them the stories, and that really sort of encourages proper understanding.
Yeah.
All right.
Well, thank you very much for joining us.
Well, thank you. That was fun.
It was. Join us again next week, and then it's almost time for school holidays after that.
Oh, absolutely.
Heaven.
Yeah. Well, it's just catch-up time for me. I don't know about the teachers out there.
I'm sure as well. thank you for joining us. Goodbye.
Thank you.
Created using Powtoon.